Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much for the patience. Thank you for waiting. Actually, I was thinking it's kind of the other way around. Sometimes the speaker shows up and we kind of just wait for 5. So it's interesting. But anyway, hey, thank you very much for being here. It is my pleasure to welcome Per Gunnenberg here. He's visiting us from Uppsala University. He's actually a visiting scholar in UC Berkeley these days, and so it was quite nice that he was close by, and we were able to make this happen. He got his PhD from Uppsala in 1983, and he got his master's from UCLA. He was he's been very, very active in this field, in the field of wireless networking and sensor networking now. He's been sort of telling me about some of the projects he's been doing, and he's going to meet a lot of you, so that's good. You can ask him about that. Professionally, he's been very active. He was, if some of you remember, if you came to Mobisys last year, he was the general chair. It was a remarkably well-done event. And he's also on the advisory committee of ACM SIGCOMM. He also founded a company called OptiMobile, and if you have some time, I've requested that at the end of his talk that he would, we will go off of the recording mode, and then he can tell us a little bit about what this company does, and because they've had some good traction with some big players in the market. And that's it. And at this point, I will just welcome him aboard and to let us know what he's been thinking about in Adhoc networks. Come on in. Thanks.
Thank you, Victor. It's great to be here. It's the first time at Microsoft Research. And it's also a pleasure to be here in Seattle. It reminds me a little bit of my home country. If you don't know where Sweden is, we have the same temperature as you have here. We have a little bit less rain than you have. This is not Sweden, so that's Sweden. So, but the Vikings, the Norwegian Vikings went that way to this country over here. So the Swedes and Norwegians one that really went to US first. Okay. Uppsala is one of these old cities, and it is quite north of Stockholm. Stockholm is here, and it's plenty of lakes here. As a matter of fact, this area, by the time we have snow up there in Greenland, we have also ice cap here in Sweden, which means that the city I live in, Uppsala, which was basically a site for the Vikings. And this was ocean by the time, and my house is right here. And that was beachfront about 1,000 years ago. I don't have any beachfront anymore.
Alive then?
Barely. Nevertheless, we got winter time, and our university, which is called Uppsala University, is one of the old ones. I keep on reminding our American friends when Columbus came to this country. We already had a university. This is one of the buildings. Some of you have seen it before. This is where I'm sitting. So now I got a feeling for my geographical location. My group is about 10, 12 people. It's been the same size as the network and research group here. And the research activities we are involved in, I'm involved in, is now we got a big grant last year, which is about $3 million a year for each year. We got, and for 10 years. So I'm building up a wireless sensor network center of excellence, similar to what they're doing, for example, UCLA Sense, also multidisciplinary in approach. I'm also working in opportunistic networking in a project called the Hager project, together with Jan Krakow, Christophe Dio, Jean-Yves Bedek, Marco Conti. It's a high-profile European project. Today I'm going to talk about the work we have done for the last 5 years, building ad hoc test beds. What are the problems? How do you make them repeatable when you do experiments? and what kind of results can you get out of them that are not visible in simulations. The other things we do is heterogeneous networks, peer-to-peer, putting in a mobile phone in a peer-to-peer network. What does it mean in terms of bandwidth, limited devices, low distribution? And we also do some self-configuring of security for small devices. So these are the research activities. In terms of my personal activities, I've been involved in a startup company for the last 3 years called OptiMobile. And what we do is basically take a regular mobile phone, like this one. This is the Ericsson P1. And this one is going to be equipped with our software. And it's a VoIP software running exactly on this phone. There's one interface, there's one address book. It's completely integrated. On top of that, when you have Wi-Fi coverage, use Wi-Fi, and it's astonishing because the quality is much better than the regular phone. And when you're losing coverage or the quality goes down, we do a handover, a seamless handover to the cellular network. And normally people don't realize, they don't hear the gap when you're making a transition. What they realize is that, wow, the quality of the voice is not as good as previously. We run it on the Ericsson P1, and we also run it on mobile 5 and 6 platforms. We have collaboration with HTC, HP, iMate. What's also interesting with the approach is that the seamless handover is done transparently to operator. That is to say that an enterprise could have the server and can choose the operator in terms of cellular networks. So they actually can choose the cheapest one, so we have a least cost routing module within it. We also have a model for the operators. As you may imagine, the operators are kind of hesitating towards this technology because it's taking market. So we have one product also for the operators where they integrate into the network. And that is what we call the IMS VCC technology. I'll be happy to tell you more about what we're doing there more in technology. We're doing in the startup company, but my focus of my talk today is going to be about our Adhoc testbed. So the background to our Adhoc testbed was the observation that the many protocols, both the proactive one, WLSR is an example of the proactive one, as well as reactive one. And the results the people coming up with this one is basically based on simulations. There are very, very few real networks and results captured out of real testbeds. So these dots here are significant. We would like to come up with a testbed that follows the reality as close as possible. So the way we thought about doing this is to have people carrying around laptops with 802.11b's. So you plug it in, you run your routing protocols on the laptop, and what we were interested in particular is indoor environment. Indoor environment, you know, it's much more complicated in terms of radio propagation, but it's probably the most common situation where an ad hoc network is going to be used. So indoor means that it's very hard to model in simulations, and you will see that the simulation models will fall short of the indoor modeling. Okay, so how do you do when you're doing experiments? Okay, here's the laptops. You got a card here, 802.11b card, and you bring in lots of beers, lots of sandwiches, and students. And you first ask them to walk around with the laptops. So what we do is setting up here the routing protocols, all the testing stuff on the laptops, and asking to move around. And how would they move around? Okay. What we'd like to achieve is the following. We would like to run OLSR on one experiment. We would like to run DSR on another one, and AODV on the third one. And we'd like to compare the results, which means that these students need to run around in the same pattern. So here is an example where they're running around in a corridor. There would be a handoff somewhere at that point. Okay. What you have seen here is that we have an execution environment. We spend a lot of time to making sure it runs both on Win or on Linux. And we use scenarios based on choreography to ensure that the students move around in the same pattern. We create a lot of interest in it in the testbed, and lots of people have been looking at it. So, the way we do it is the following. For each laptop and student, there is a script, and the script is giving choreography, where to move and what time. So what you can see here is that test is starting, that the green one showed on the laptop, and we're starting a daemon to collect information, data, and the red one is the duration, 1 second. Students, that student here at node 11 should stay at this location, and after 30 seconds, the red one, start moving, go to point A, the end of the building. After 75 seconds, you should arrive at point A, please stay, and so on for the whole scenario. So this is the basis for us to create some kind of repeatable mobility pattern. Of course, it's due to the fact that we have stochastic effects here. Because people are moving around, they don't follow the correct path. In the corridor, you can't move side by side sometimes. So there is a lot of statistics around handling the information, the results we're getting out here. So the way we do it is the following, that every node is collecting everything it can hear. Every event is time-stamped. And all the receive packets are collected at all nodes. And we're taking snapshots. Why do we do that? Okay? Because we do all the analysis done after the session. And the reason is the following, that I would like to figure out the connectivity at every time instance. Because the routing protocol should react to the connectivity changes. How do I figure that out? I can't have one listening in the middle, because I don't know what you can hear, if you can hear that one or not. So it's a completely distributed system. So the only way we can handle it is take the complete pictures that everyone is listening to everyone. And then we do an analysis afterwards and figure out the connectivity. Giving them the routing state, we can look at the connectivity, look at the routing state, say, okay, this routing protocol really didn't do its best because it was a much better path somewhere else. So that's the basis of it. Okay. Given that we can collect the connectivity, we also collect the signal to noise ratio for each connection. So what you see on this picture is the time for different type of connectivity. So the scenario here is basically saying to the students that there should be two groups. They are moving to each separate part of the building. So after 25 seconds, they start to move around. The distance between these edges here, the longer distance, the lower the SNR value. So for this picture, for example, here they're completely separated, but the students here are in two separate groups. Of course, they have connectivity at that point, and we go on, and they're getting together again. Okay, here's an animation. So we collect in this one the traces. And what you can see here is basically animation here, that we put out the signal to noise ratio, the students here, You can see this kind of movement, that is change in the signal strength is basically due to people standing there and talking with each other. And so they're shielding the laptop from each other. Here's the time, 26 seconds, 27, and this should start to separate at this point. So here you can see that I think number 4 is doing something. I don't know exactly what she or he is doing. But you can see now they start to separate. What baffled us in the first time we saw this one was all these sporadic type of connectivity. It's due to the buildings. And you can see sometimes it comes and goes very short times, these connectivity. So lots of connectivity changes, much more than they expected from the beginning. And you see there still are some sporadic ones. And it turned out that you will see that these sporadic connectivities are really screwing up some of the routing protocols. Now they are separated and they're going to go together again, and you will also see the same pattern again. Yep.
You said the connectivity was more sporadic than expected.
Yes.
Just wanted to get a sense of like, what did you expect?
We'd expect that you will see that when they are separating, they will gradually, more slowly disappear from each other. I didn't expect when they are separated this one that you have a sporadic one and then it disappear again. It's probably due to the fact that people are moving around a little bit and you have the corridors act like a waveguide. You see that it's starting to get together. Okay. So what you have seen is basically this one. In practice, to make sure that you have same pattern or movement, you should compare all the instances of this connectivity. Of course, that will not be completely identical. But what we try to do is to look at it from a statistical point of view that they are identical enough. So you have a more confidence interval. And sometimes it gets stuck at this point.
It's an x86 Maggie.
List on it.
Couldn't hear.
It's true in theory, it doesn't work.
No.
I don't try it. You're talking about using bootcamp, right?
Yeah. It doesn't work. What's wrong?
This laptop doesn't like me right now. I don't know why. I'm going to disconnect the video output so people know that. So let's see if we can get it back here. Sorry about this one. I think we are back in operation. Okay. So this one is basically summarizing what you've seen, what we believe our testbed can be used for. Relative protocol performance, comparing two of them. Seeing the radio channel effects. Interactions between hardware and software, which is very important from our perspective. And I'm going to show you one example. It's called a gray zone. We use it for validation of simulation models, taking our results and move it into NS2. We have used it for generation of traces, so we can, yes?
So if you have a specific recording of people moving around and all the connectivity at any given time, could you use that to simulate what a routing protocol would do?
Yeah.
Would that be as good as having the students run around for 100 times with different protocols?
Sure. What we did is taking this one, for example, we take the students moving around, taking the traces, moving into NS2. And we were also able to recreate some of the problems you see in the regular simulation models by using the traces here. So that's what was an idea with our experiments, to making sure they validate the simulation results. I'm doing this one because we would like to see if we can do orthogonal testing, that we can show the same results both in the real world as well as the simulation. So one of the things that we, for example, here we came across first was the fact that 8.11b is creating what we call a gray zone, that when you do a broadcast, you do a lower bit rate, you're reaching further than the unicast. So some of the protocols do rely on the fact that you do a broadcast, this one is doing a broadcast, and to detect the connectivity. When you start to send, you use a unicast higher speed, and you drop in packets, which results in the fact that you do a new broadcast to figure out the connectivity, and you reach further. So that is causing problems when you are getting in position, setting up a path, and you're getting into position for number 1 here, that is in the gray zone. The world is not as simple as a circle, so it's more complicated, of course, in these kind of complicated environments, very difficult to predict. So the gray zones do really vary. The way we handle this one is basically to be more conservative with the broadcast. We say that if you have a signal-to-noise ratio below that value, we discard it. So that is to making basically the reach not as wide. Okay, I talked a lot about making things repeatable. I told you about how we use your choreography, and now we have a question.
So the recent thinking on gray zone and things like that is to use routing protocols that leverage diversity in some way, like the XR protocol or other protocols that are coming up. Did you look at any of those, and do they really help in practice in dealing with gray zones?
We haven't looked at that one. What we did more conservative, and it worked out pretty good. You lose a couple of meters in reach, but who cares about that?
Like 2 meters wide is what you're saying?
It is. It varies from our measurement between 1 meter and 10 meters.
Okay.
You can't predict. So what we did is working best is to use basically be more conservative. There are other ways to handle the gray zones, but that's the one we eventually settled. Okay, we talked about the choreography, and of course there are variations in hardware and software configuration. We started up with heterogeneous laptops, and we quickly ran into problems to understand where is the problem. Is it in the laptop? Is it diversity or not? So the hard thing we learned from this one is that we need to keep things much more simple, both in terms of mobility as well as the experimental environment. When it came to seeing if the connectivity pattern are identical, we came up with a visual tool saying, okay, this looks very identical. I don't think you can barely see that. Here is basically the accumulated signal-to-noise ratio for one experiment to another. We got one peak there. And the peak here is quite similar. You can do statistics on this one. What we ended up eventually was to look at the results, and we ran every experiment about 10 times to get better statistics. Okay, getting into the second part is showing some of the results we came out of this test bed. And the first one that we decided to do is to look at much more simple scenarios. You saw the complicated one here, that we have lots of students moving around. Interesting, but we couldn't figure out what's going on. And what was the problem when we're starting our and running TCP and IP, UDP over it? So our ambition for the next step was to create, as I mentioned here, that we had a real world. We would like to create also an emulation environment. We're still using the same routing logic, same hardware, same stack, but of course the mobility here is not the same as the real mobility. We try to mimic that as close as possible, and that also applies for the simulation, which you can see here. So that's our idea, to do all three of them and then to compare the results in order to figure out where is the problem. Looking at the protocols here, Shall mention that OLSR is proactive, which means they're keeping track of all the connectivity at all times and try to figure out a new path. AODV is a reactive one, which is basically setting up one path to the one you communicate and don't care about the connectivity around that path. So it tries to maintain that path as long as possible. DSR is more aggressive. It even listens in to figure out if there is an alternative path that is smarter. So we're starting up with a naive belief that DSR, which is more aggressive, listen in, should do better. So emulation was very simple. What we did, basically setting up our laptops with our protocols, and we used MAC filters to force connectivity changes. So it was perfect connectivity change with these MAC filters, but they appear basically at the same time as our choreography. So that's why we keep it similar. Still, it's important to understand that we have external radio interference, but we also have internal interference between these two, so it's very different towards the real environment. When it comes to simulation, we discussed a lot about what kind of radio propagation models we're going to use. We settled for the standard ones, and you should know that some of them are better, but they're still simulation models. So what we did also for the NS2 model was to tweak the transmission range to better match the indoor environment. We put in a mobility model. We don't use traces here. The mobility model, we put in some also on jitter to mimic the movement. Run 10 results. And as you can see at the bottom, our question is, how well will the simulation do? If you look at the comparison, the amount of it, free managed protocols, free traffic types, free mobility scenarios, we're going to talk about them, and free environments, simulation, emulation, I mentioned that one. For the real world, we run a lot of experiments. You can see 270 runs, having students running around 270 times. So we only have graduate students which we pay eventually to do these kind of experiments. And they would all of them taking place in our office environment. I can refer to A, B, C, and D as waypoints. And the laptops here is going to be number 0, 1, 2, and 3. And all the information here, which I'm going to show right now, is going to go from 3 to 0. When we saw this first picture, the animation, we were baffled by the amount of connectivity changes. So we decided to come up with very, very simple scenarios that is easy to understand, but still triggering some of the constructs in routing protocols that are crucial. Okay, so the first very simple one, which we call the relay node, is working with this one. You establish a path, setting up a path between the nodes. And at some point in time, the students, and this is 1 and 2, are moving and switching places. That's why we call it a relay node swap. At this point, you can see that we have only 1-2 hops between 0 and 3. But it could very well, depending on the situation, the protocol could go this way. So this depends on how well the protocol adapts to the situation, and that differs between these protocols. So that's objective with it. And here's the timing of this one. I'm going to use this one, saying that the relay nodes are going to change after 81 seconds, take 101 seconds before they have switched. This is the speed, 1.3 meter per second, which is the walking speed. The other one is, which is stressing, is right here, is that not only the relay node are moving, both the receiver and the sending are moving in this context. So this, you're ending up in a situation that you can have a connectivity look like that or that, depending on the radio situation. So different protocols can cope differently with this one. And here's the timing. Let's skip that. Getting into the third one, which we did, is called a roaming. That means that the protocol is getting over to point B, setting out a path, to C, setting a path, to D, setting a path, and then going back again, roaming. And this put some stress on the protocols to figure out how long time should it hang on to one and when should it shift to the new one. Because in this situation, you may hang on, some protocols hang on, some protocols figure out go directly to point B or to point A. And then you're getting to this point. Look like that. Results. Okay. So these are the results from the relay nodes. These are switching places. That's the only thing they do. Very simple. Here is, we run UDP, and here's the delivery ratio. One is perfect delivery. This part is simulation, this part is emulation, and this is the real world. These are different protocols, AUDV, DSR, OLSR. And what you can see here is that in simulation, OLSR is not doing as well as the others, because it doesn't react. It takes some time for OLSR to really figure out the connectivity. And when it's a connectivity change, it's losing a bit. And you can see for emulation, it's consistent. The real world is not consistent for some reason, but it's within the variations. So we have a variations about standard deviation about that size. But what is consistent is that the real world is consistently lower than what we have for emulation and simulations. And if you go for TCP, wow. If you do an AND swap, these two are trading places. You see the same tendency, but you can also see there are some variation. None of them is better than the others. But you see also for TCP, you're on the losing end. Similar pattern for if you do a roaming node. And it's also very difficult from these results to conclude that one protocol is better than the other. It depends on the situation. Probably it depends more on the stochastic effects around it. We open up the box, try to capture time by time what's going on, and you see the time here for what's called the N node swap. These two are swapping. You see the time here starting 51 seconds. Here is the number of seed UDP packets. What you expect, perfect, they're going to be a linear growth like this one with the time. And you can see that is the case for simulation and emulation pretty well until time 100 is basically when they had traded places here. Then there is a little bit of disturbance. But for the real world, you're losing from the beginning. Like this one. And it's a plateau here. It takes some time when the routing protocol is basically blocking what's going on there. So it has to wait until it gets stabilized before you can start. And this is significant. This is seconds. If you look at another protocol, it's the same tendency. This is OLSR. You can see it's another plateau there around 60 seconds. And that's due to the fact that OLSR takes more time to find out a new path. Look at simulation for TCP. And this one is also the switching between A and D. What you expect in this context is basically following what we see in the simulation. We started up here. It is linear because you have 1, 2, 3 hops in the beginning. It's linear like this one because you have interference between the nodes, and that's part of the MAC protocol. And when you only have 2 hops, you should be increasing as expected and then level off and going in the same linear direction as in the beginning. So these are different protocols. Don't care about this one, but look at what happens in the real world, that AUDV is basically stalling until 65, 70 seconds, where it's landing on 1 or 2 hops and then making progress, and then losing packets again and getting stalled. And you see the stall time is considerably long here. They're making very, very little progress. While OLSR is making better progress. So OLSR is more stable. It's simpler, but it's more stable. So it's making better, but it's the plateau here. So.
In reality, that second graph was a lot lower, right?
Yeah, exactly. This is much lower. If you look at the other one, the pictures here is much lower than the picture one. So you lose so many packets in the beginning. If one protocol performs better than another in simulation, it's possible to assume the same for the real world, and the answer is yes. Oops, too fast. Okay. Ping. Ping between 0 and 3, and you had 2 of them switching places. Here's the simulation. AUDV do very well. OLSR do very well. DSR is a little bit of a delay until you get to the real world. We didn't believe this one when we saw it the first time. DSR, which is more aggressive, should do better, right? It's listening to the best path. So what we can see if we log it with the time, that DSR is building up a queue like this one, so you got a delay here, about 10 seconds delay for DSR. So what is the reason for this? Well, when we dig into this one, what we see, what happened to DSR, which we call flip-flop routing. And this is the way it should be illustrated. If you look at the simulation part, this part first, here's the time as before. Here is the connectivity pattern, 3210, which is the starting point, 3210. So the red is a packet here. So it should work very fine until a point, whatever it is, 85 seconds, 81 seconds to start to move. And then suddenly you have another path, 320, because they are moving. So here you can see the connectivity pattern. In reality, it looks like this. So here's a 3, 2, 1. There's stalled here for some reason. By getting to this point, what you will see here is that DSR, by listening quite frequently on new paths, and you see the sporadic ones coming up, and DSR is, oh, I got a new one. I'm going to go for this one. And then, oh, I dropped a packet there. And I'm going to go for a new one. And it got installed. So this one is basically flipping back and forth, creating lots of routing information. And since DSR is basically buffering the packets while waiting to find a new path, it builds up the queue. So that's why we got this long delay. So you can see that going back and forth. This figure we tried to illustrate how agile the protocol is to topology change. OLSR is the most conservative, DSR, as you can see, is the most aggressive, ADV is the one that is, yes?
How much of this is implementation specific? I mean, does your AODV also buffer packets, or is it just changing the routing table on the fly, and any packets just happen to go out on whatever route you currently have?
Right. It's part of it is implementation dependent. Part of it is dependent on the kind of the timeout you're using to detect and not detect it. So that is also dependent on the implementation.
What is there a buffer on AODV?
What you can do is you can clean out the buffer.
I mean,
on AODV, it's not a buffer in the same way.
It is or not?
No, it's not. No. So what we did, we modified DSR to take away them these problems, and we were able to do much better for DSR. And take away the caching mechanism that DSR is basically running. What we also did was to implement these effects, also the flip-flopping in NS2. And we were able to recreate this pattern with flip-flopping which we have in the real world. So that way we were able to calibrate that this is real effect. But it's true. Many of the DSR implementations you can squeeze it. But the problem where I see it is that this is also application dependent on the context, how you set the parameters. So it's not one parameter that fits everything for DSR. So we can squeeze the parameters with this very simple scenario which you have here and get it much better. What we see here is the black one is basically the 1 hop, 2 hop, 3 hop, the way it should be. The red is lost packet, we don't care about that. The blue one is the interesting part here, because blue one is indicating there is a better path at this point the protocol should be taking. So OLSR is slow to react. It could do better for this one, switching to the other 1 hop. DSR is going back and forth as we expected. AODV is hanging on too long, unnecessarily too long to a path. This is the blue indicating here. So if you look at the routing control overhead for this one, and this is the ping, you can see as expected that the DSR routing overhead is skyrocketing at some point. Okay, getting to the conclusions. So our objective was to design a test bed that is as close as possible to the real life, with all the problems of repeatability, reproducibility, real hardware, and so on. We're ending up looking at very simple scenarios. And look at these simple scenarios, we do worry about how would it scale up. What will happen when we have more mobility? What will happen when we have vehicles coming into play, for example, with these protocols? I hope that I also have demonstrated the value of doing cross-evaluation of different environments, and also demonstrating some of the results we have revealed with this one that are not visible in the simulation. And are you also worried about wireless technology? Some people are apparently that. So,
I have they're kind of random because they were questions I had earlier, but I'll ask you anyway. So you made a comment about heterogeneity and trying to be very sort of clear about the kind of software and hardware consistent across the thing. So that's fine. But you were also talking about the real world, so that's not fine in real world, right? You have to deal with heterogeneity. So it would be sort of nice to sort of see that the effects you see, I mean, you can constrain the environment and you see certain effects to compare these routing protocols. But then it would be nice to sort of see if you did have heterogeneous environment, the results or the conclusions you drew from your homogeneous, do they still stand with heterogeneous environment? Because that's where we really are. Right? So that's point one. The other thing is that to me it seems that, I mean, every time I think about this thing, is sort of like, I was thinking about the stuff that we did, and in our case, we didn't really worry too much about mobility because our nodes were static. And the question, I mean, it sort of seemed like DSR was a fine thing to do. And obviously, I can't conclude that from you because I don't really know. You didn't really do those experiments, but it seems like there's this other layer, intelligence layer that you now need, which is going to adapt either between the routing protocols themselves. So you have multiple routing protocols implemented inside your stack, and you adapt based on what the environment is. So if you have more mobility, you do certain things, or you change the parameters constantly. And perhaps that's where the research should be focusing on, not having to worry too much about constantly redesigning these new protocols, but essentially taking a few which are very promising and then being adaptive on the layer above them. So do you have thoughts on that?
Again, comments on it. Let's take the heterogeneous question first. Of course, you should run the heterogeneous to try to figure out if it's some specific in the hardware. And I put up the table that you have same hardware, you have the same logic, and it could also be a table saying that you have a different hardware to figure out if there is some specific in this hardware. Based on our experience, I would not expect that the base results here will be changing, but we don't have any conclusive results showing that. So that's the first one. Getting back to another question of how well the routing protocol will do and if we can squeak them, if we can replace them, I think it's important to realize that the problem here is basically due, the way I see it, is due to the mobility. In a meshed network environment, you don't have these kind of problems. So the second, one of the big thing here causing the kind of problem is 802.11b. It's poor for ad hoc networks. So I think that is one thing we need to rethink about. Third lesson, I think that keep it simple, stupid sometimes is the winning track. And you don't need to be that aggressive. It doesn't make sense in the kind of environment you are in. The third question is, how do you do ad hoc network? We have been starting thinking about opportunistic networking. Maybe we should do the other way around we do today. Today we try to mimic the path, basically, and put the routing protocol above that. We tried hard to get a path because we would like to use our end-to-end protocol that works so well on the fixed internet. If you do it the other way around, say, okay, the common situation is going to be disconnected, sometimes connected, sometimes partially connected. How would I design the protocols and see the internet fixed environment as the exception? It's a beautiful exception, but maybe our system will work better. So these are the kind of things we've been starting to think about right now, and we do that in terms of the Hagel project, opportunistic networking. Because I get worried, I mean, even these very, very simple ones, we try so hard to get a path up. Did I answer your question?
Yeah, you did. Okay. Although I was sort of thinking if you go to the opportunistic routing, you might actually see the flip-flop behavior that you were seeing at DSR, because in some sense, that's kind of what it's trying to do.
Yes, it does.
Opportunistic.
Yes. Because the dynamic parameters outside, when it's difficult to control, and how do you turn it up?
I was wondering, how much do you think that the differences you saw are really due to the routing protocol in particular, or the metrics that the routing protocol are implementing underneath? Because at least in our test beds, we found we could get radically different results by changing the metric, that whether we considered a route either just up or down, or whether we considered what its bandwidth was or what its loss rate was,
Right.
And having varying degrees.
Right.
And also, parameters like how long do you stick with the route after
Yeah.
you think another one's gotten better?
Right.
I mean, do you immediately switch? Do you
Right.
have some hysteresis? I mean, all those things to me seem to play in a lot more in terms of how they compared, because we ran our test bed also with AODB as well as our own variation of the base
Right.
link quality based on DSR.
Right.
And we found that the metrics was far more important actually to the behavior of the
So
test bed
what do you mean metrics here?
protocol. The things I just said, whether or not you consider a link to be up just if you get any packets through, or if you get 90% of the packets through. At what point do you start telling the protocol that it should switch routes?
Yep.
I mean, and how quickly does it
Yeah.
react? That's what I mean by
That's a very good question. So the what you see here is that effect of the gray zone, and it's actually the gray zone when you have all these sporadic ones, and I can make it much more conservative. But since I'm moving in this context, sometimes I'm going to get in a zone that have fluctuating because of the reflections, because of the buildings act like this one. So you may have, even if you make it more conservative and say I don't switch routes until I have that high level of signal to noise ratio, you may end up in the building. That's what we see, that okay, due to the reflections and the radio propagation, suddenly it appears anyhow. In some way, I would like to have a mechanism saying that I would like to filter out the short ones because they are screwing me up. So you're right, you can screw in the parameters here. But our experience is that you can never completely get rid of them. So you get more conservative. Yeah,
Just to follow up, were your cards set to auto rate or were your fixed transmission rate?
it's auto rate. Yeah, we tried to do it in a fixed rate also, but we did that 3-4 years ago. What we ran into a lot of practical problems to fixed rate, and that was basically to gray zone problems. Yeah.
So, study the chart, with static mesh network, what we found was that factors such as where the nodes were and what hardware they were using and what the workload was actually impacted the performance far more than the routing protocols or the routing metrics.
In a mesh network, I would expect the
In your
same.
case, presumably the factor that affects your results the most is mobility, and you
Yeah.
can't control for that. But did you repeat your experiments with different kinds of hardware, for example? And auto rate actually, Brian is a great point. So if you had suppose set the rate of all the packets to be 6 Mbps, how do you know that a large number of these problems that you're seeing are not simply because the auto rate algorithm is being too aggressive? And what was the what was the underlying packet loss rate?
I don't remember. That was not a concern for us. We did take measurements on the underlying, and if I understand you right, underlying and loss rate.
Wouldn't most of the gray zone problems just go away if you used it at the lowest transmission rate?
Yes. No, it will not.
Why not?
Because in the building, it doesn't look, in the building you have reflections and you acting as a waveguide sometimes, and sometimes you have connectivity and sometimes you don't have connectivity, even if you screw down and make it more conservative.
Well,
Yeah, you can make it very conservative and then you,
But unicast would match broadcast, right?
yeah, that would disappear.
That was the definition of
That would disappear.
Yeah,
So the
your
gray
gray
zone
zone would go away.
The gray
Yeah.
zone does go away.
So for experimental results here, we basically tweaked it, take away the gray zone. But we're still ending up in the fact that when you have mobility and you're moving inside a building, you have still varying connectivity. So for all experiments here, maybe I didn't say that, we took away the gray zone effect that I showed you from reaching further.
Did you try? Sorry.
Yeah.
Did you try different hardware just to see what the impact of the different hardware was?
Yes, we tried different hardware, but we haven't any conclusive results on it. We're running out of money at this point.
They might now.
Yeah, I'm running out. More questions here?
Yeah, in one of your experiments, you show that there is two group of people separate from
Yep.
each other. And based on this scenario, I guess some people propose that you can let a group of people collaborate together and make a mind mode transmission to the other group and then decode on the other side. So from your experience, how practical is this thing at this moment?
You saying you mean from one side to another with MIMO?
Right.
I don't think the objective was for us to... Our objective was to look at the protocol, how to behave under variant connectivity. And you can do... some people have been talking about MIMO and making sure that you have a better connectivity. I'm personally, I don't believe, but I'm a little bit skeptical that it's really useful in a mobile environment. This one. Someone are protesting here, yeah.
You brought up like reflections as like a major cause, it seems like, when you're answering. Do you have any empirical evidence to suggest that like in the indoor environment reflections actually matter? Because I would have thought like...
I don't have any empirical evidence in our experiments. What I do have empirical evidence is the variation of signal strength with when you're moving around in a corridor. We did a lot of measurements and moving very slowly and controlling to see how the signal to noise ratio vary.
That could be just the normal shadowing that happens.
It could be normal shadowing, it could be reflections, it could be all these parts. Our point was not to... Our objective is not to refine the radio propagation model, but to see how the protocol could react in this kind of environment.
We do have some empirical evidence internally. We had this company, I forget, which had the first MIMO chip show up, and we tested that internally, and we did see that the ranges of those NICs were far superior. And that was primarily because they were using MIMO.
Oh no, so that's different from like the card being impacted by multipath reflections. So it was a different question in the sense you got basically one real signal and one reflected signal. In the indoor environment, is current .11 hardware actually vulnerable to that? I thought it isn't because the delay is very small and the rake receiver does pretty well. Where reflections actually hit you most is in the outdoor environment if you use Wi-Fi equipment there. So I was just curious, like, since Per was pointing at reflections, whether or not they actually impact or if they've observed anything.
That's my understanding too, because it's such small distances.
Right. I have a different question too. This goes to us like to just building research testbeds. Do you think this method is actually practical? Like, what's your experience been so far in terms of like building research testbeds? Is this the right way to go?
I think that we need testbeds, but there is a large spectrum of testbeds, and I say that we probably at one end of the spectrum, and you can have simulation at the other one. You can have emulation in the middle, but also there's a large different type of testbed you can use for different purposes. So I think that the most important thing is to understand what is the limitation of each testbed, what you can show with it, and these testbeds. What I feel intrigued by is the Genie effort. How could we come up with a wireless testbed attached Genie that makes repeatable results? And how do you do that?
Right.
Yes.
Do you have any thoughts on that?
We just started to talk about it. And one thought in my mind is that if you want to have repeatable mobility, I will probably do as you do in UMass, put it on buses because they have regular schedule going around, the same pattern.
Right.
And I mean, other people would like to have laptops putting students and they can move around freely, and you look at the random type of movement. So there are different thoughts on it, but these are thoughts on it. Yeah. Robots, yeah. Rice is doing robots.
Did you found that the students were able to repeatedly do the movements that you wanted? Or well, I guess the question I'm asking is, would robots be better than grad students?
Yes. They would be better than grad students in terms of repeatability. The grad students add a sense of reality to it. And I see. And the robots in some way are also constrained when they're moving. RISE is doing robots. So they're complementing each other. I can talk about the company, yeah.
Okay, so we're going to wrap this up. So thank you very much for this.
Thank you.
So what we're gonna do now